All right, this week the course had a little less material in it than some of the others, but maybe people were ready for a little bit of a break as we come into the home stretch. But nevertheless, let's take a look at what the most important concepts were. So first, the entropy variation associated with a change in temperature can be expressed as the heat capacity either at constant volume or at constant pressure, depending on what kind of a system you're looking at, divided by T. And just as integrating heat capacity can be used to determine enthalpy, the integration of heat capacity divided by temperature is used to determine entropy. The third law of thermodynamics says that at non-zero temperatures, all substances have positive entropies. At 0 Kelvin, the entropy of a perfect crystal is equal to 0. An entropy of exactly 0 depends on there being a single non-degenerate ground state. So if the ground state has some degeneracy, you still might be very, very small, but it won't be exactly 0. Exactly 0 requires a non-degenerate ground state, for which case W, the measure of disorder, is equal to 1, and also the probability of being in a given state J is the Kronecker delta Ij, where I indexes the ground state. So I actually used 0 as that index earlier this week, but in any case there is one state with probability 1 and all other states with probability 0. I told you about the research of Professor William Joch, who generated temperatures very near to absolute 0 using adiabatic demagnetization, and that process allows you to go beyond the lowest temperature that's achievable from adiabatic gas expansion and really come arbitrarily close to absolute 0. Calculating the entropy through this integration process that I just mentioned from the last slide can be written mathematically as entropy at a given temperature T is the integral from 0 to the melting point of a heat capacity of a solid plus an entropy change associated with melting, plus another integral from the melting point to the boiling point of the heat capacity of the liquid, plus another phase change, now vaporization, entropy change, and then finally to an arbitrary temperature T of a gas, integrating from the boiling point to that temperature the heat capacity of the gas over the temperature. Rather than having to start exactly at absolute 0, this process can be facilitated by starting at a somewhat higher temperature, still cold but higher, and noting that the molar entropy at that temperature ought to be equal to the constant pressure heat capacity at that temperature over 3 because of the Debye T cubed law. Entropies that are measured in this fashion from experimental measurements are in near quantitative agreement with results that would be predicted from the partition function using S equals K log partition function plus KT partial log Q partial T at constant number and constant volume. Something I don't know that I said when I presented all this, by the way, is we tended only to make this experiment for gases. And that's because we actually have a pretty good way to construct the partition function for gases. Many of them behave nearly ideally. You might remember that you saw a correction for nitrogen that was very, very small. So at the temperature and pressure we were looking at, it was pretty close to ideal. Now, while we would still expect to see this near quantitative agreement, say, for a liquid, the trouble is we might have a much more difficult time coming up with a good partition function for the liquid. And that is not the subject of this course, but suffice it to say that can be quite difficult. But in any case, if we get into the gaseous regime, we are golden with statistical molecular thermodynamics. In terms of the degrees of freedom that contribute to entropy, ordered by quantitative importance, the translational energy levels and the ability to access many of them contributing to disorder contribute the most to the entropy of a substance. The rotational levels are next in importance, vibrational are lower, and electronic excitation even lower. These last two, in many of the examples we looked at, made virtually no contribution at all. So this last greater than symbol is somewhat notional in a way, but translation dominant, rotation often very important. Again, really gases we're talking about here, In other condensed phases, we'd need to talk about other phenomena associated with motion. As a particle's mass increases, the translational entropy also increases, and it does so in a logarithmically with the mass. Very stiff insulating solids, like diamond, have very low entropies near 0 Kelvin, and conductors get to low entropies much less rapidly because they're conductors, because they have electronic motion that needs to be considered as well. We also looked at larger molecules than just, say, monatomic and diatomic gases, and in general, the more atoms a molecule has, the greater its entropy at a given temperature, because generally that additional number of atoms will bring in increased mass, larger moments of inertia, and perhaps degrees of vibrational freedom where the vibrational temperature is low enough that they begin to contribute some disorder of their own. Residual entropy is a phenomenon that can be associated with a system that fails experimentally to access a perfect crystal at 0 Kelvin. And I used the example of carbon dioxide as one system that exhibits that kind of phenomenon. Just as was true for enthalpy, or is true for any state function, the entropies of reaction are additive and derive from the entropies of products minus entropies of reactants. And last of all, entropies of gases are much, much greater than those of their corresponding condensed phases, and we saw that when we looked at some specific examples of entropies of reaction. All right, well, we have reached a stage now where we have actually covered all three of the laws of thermodynamics, the first, the second, and the third. In the last week of the course, we're going to take advantage of all of these laws to look at two additional thermodynamic state functions and the relationships between all these different state functions and what we can do taking advantage of these relationships. So the first of those state functions that we'll look at will be the Helmholtz free energy, and we'll get started on that next week.